Okay, good morning everyone. All right, so how's everyone today? Feel good?
Yeah.
Okay, that's great. Okay, so
Yeah, the
all right, so last Tuesday, so we already finished with the chapter one. Okay, and the chapter one discussed about the SI units and also about the vectors. Okay, so now we are in the chapter two. So we're going to discuss about the motion. All right, so before we going further with 2 and 3D motion. So first, we look motion in the one dimension, all right, which is along a straight line. Okay, so this this chapter won't be hard because it's basically it's a revision of your pre-university physics which you learn during the matriculation, right? So let me share the slide. Okay, you can see my slide.
Yes.
All right.
yes, Doctor.
Okay. So basically, in this chapter, uh, so you will learn about the displacement, average velocity, okay, and then what is the instantaneous velocity, and then about the average acceleration, okay, and then about the free fall object, all right, and then lastly about the how to analyze the straight line motion, okay, when acceleration is not constant. Okay, so here, so the definition of motion is about the kinematics, right? So kinematics is a study of motion. So whenever people ask you what is the kinematics, so kinematics is about the study of motion. And in kinematics, the velocity and acceleration are the important physical quantities. All right. Okay, so when you're running, let's say you join the marathon, so you will change your speed, right? So that's according to your willingness to change or depends on your body condition. So if you feel tired, you might want to decrease your acceleration, all right? And then might be when you feel your body, you can push harder, so you can increase your acceleration. So acceleration uh, is actually the the variable that change uh, quickly for every time you go through the line, okay, but for the velocity, so velocity is a more stable quantity, right? So because velocity is actually the derived from the acceleration, okay, where it is the uh, derivation of the acceleration. Okay, so how to relate that? So let's say we have a particle moving along the x-axis and it has a coordinate x. Okay, so now we are at a coordinate x. So you need to imagine that, and then the change in the particle's coordinate. Let's say, so you're moving from x1 to x2. Okay, and then the change is delta x. All right, so let's say x1 is 1. Your position is 1, and then your x2 is 10. So the delta x will be 9, right? The average x velocity of the particle. All right, so because the velocity is a function of time, So you need to divide with the delta time. Meaning the delta time is the time taken from you to move from x1 to x2. Okay, so I hope that's clear. All right, so as you can see from the slide, so the average velocity is given by v avx, right? So that's the equation. Okay, so for the rules of sine of the x velocity, right? Because we are mentioning the x because we are still considering that it is in terms of the one dimension motion, which is on the x-axis. Okay, so if the x coordinate is positive and increasing, so the x velocity is positive. Okay, but when it is from the x coordinate is positive, let's say you are considering you already moving at certain speed, all right? Moving at a certain speed. For example, your car is moving from x1 to x2, but at x1, it is, let's say, 100 kilometer per hour. And then at x2, it is now 50 kilometer per hour. So that means your uh, your velocity decrease, right? So it shows that the velocity will be negative because it is decreasing. And then, okay, if the x coordinate is negative, all right, and increasing, yeah, from negative, maybe it's moving toward the positive direction. So your velocity is positive, and then when it is negative and going to the negative side, okay, let's say from -1, all right, and then it goes to the -10, all right, so it will be negative velocity. All right. Okay, so let's say we have a swimmer here. So the winner of 50 meters swimming race is the swimmer whose average velocity has the greatest magnitude. Okay, that means, so the swimmer who travels a displacement of delta x of 50 meter in the shortest elapsed time, delta t. So of course, so we are looking at the time. So whenever you can go further at the shortest time, so that give you the highest velocity. All right. So for measuring that, okay, so we have a position time graph. Okay, let's say, okay, we have at time 1. So at time 1, so your position is at x1. Okay, maybe the x1. All right. So let's say you can see on your right, so we have a dragster track. Okay, so the car is moving from P1 to point P2. All right, so we mentioned that P1 on the graph is equals to x1 and P2 equals to x2. So basically the car moves slowly. All right, the car moving slowly at 1 to 2, but it increased its speed after the time t2. All right, so when it increase the time, of course, you will move faster. All right, the car will move faster, reaching to the x2 point. Okay, but because we want to find out what is the average velocity, so we need to find out what is the slope between the point P1 and P2 over here. Okay, as you can see from the graph, it is point P1 to P2. Okay, so how do we find the average velocity? All right, so because we are looking at the slope, so the slope meaning that, so we are taking P2, all right, actually a P2 minus P1 over T2 minus T1. All right, so that's actually the way for you to calculate the average velocity. Okay, so that's simple. All right, so always remember that when average, we just taking the starting point to the end point. Okay, that's for the simplicity. All right, so they might be a harder calculation. Let's say you are given more points within that, so you might use that different points to calculate your velocity as well. But for this time, all right, we make it simple. So we just take the initial point up to the end point. So the difference between that, we divide with delta t, the time taken at the initial point to the end point, all right, to find the average velocity. Okay, now we're going to define the concept of instantaneous velocity. All right, what is the instantaneous velocity? So the instantaneous velocity is the velocity at a specific instant of time. Okay, so meaning that we are measuring that. Let's say for this graph before, let's say we have P1, and then let's say we have a P3 at the middle of between P1 and P2. Let's say we are measuring at T2. Let's say our P2 is here. All right, so let me draw. Okay, so let's say we are drawing over there and then also over there. Okay, we want to know. Okay, so that's P3. So that's actually instantaneous velocity. So we find the difference between P2 and P3 and P1. So that's the meaning of the instantaneous velocity. So because it says at specific instant of time or specific point along the path and is given by Vx. So it is equals to dx over dt. Okay. And then the average speed is not the magnitude of the average velocity. Okay, so in terms of equation, we can define that. Okay, so Vx, so the Vx is the velocity, okay, in terms of x, right? So we have the, okay, let's say delta t goes to 0, so limit goes to 0, and delta x over delta t, so at instantaneous time, so we have dx over the dt. So why do we put the limit here? Because it is equals to the limit of the particle's average x velocity as the time interval approaches 0. Okay, so as the time interval approaches 0, so we define what is the difference of x and also the difference of t. Okay, so basically when you look at the graph, okay, so we can define that the instantaneous velocity. Okay, so the instantaneous velocity is actually can also be find out similar like a average velocity, but we are looking at the specific time. So as I gave you the example before, so let's say now we have our T2, all right, so we have 0.1 and P2, all right. So before this, let's say the P2 is longer, right, at 5, at T5, but now we are looking at, okay, we just stop at 3, okay, we looked at, and then we have the delta x, all right, the delta x is between here, all right, this point to that point, okay. So for example, it is already calculated here, so the difference of x from this point to that point is 150 meter, and then the time taken for the object to travel 150 meter is 2 seconds, all right, from T1 to T2. So the average velocity is equals to 150 over 2, so that's equals to 75 meter per second. Okay. All right. So that's one example. Okay, let's say the velocity, the acceleration increases more at shorter time. So let's say we have different graph. So let's say over here, you look there. Let's say, so this is a different acceleration. So we have time. So we are measuring at a shorter time. All right. So we need to look that. Okay, we need to look that. So before this, okay. So instantaneous velocity, as I said, we also calculated in terms of the average. But let's say we are looking at the specific point. Right now, we have only t delta t equals to only 1 second. All right. And then the delta x, so the difference between x1 and x2, so let's say x1 is there and then x2 is there. So it's only 55 meter. Then the velocity, where we define the instantaneous velocity, is 55 meter per second. Okay. So, all right. So that's actually the velocity at point 1 to point 2. Okay. All right. Okay. Later, we also can find out what is actually the instantaneous velocity. All right. So the instantaneous velocity is defined by doing the tangent. So you guys familiar with the tangent concept? Any one of you? Any of you are familiar with the tangent concept? There? Hello? Hello?
I don't remember.
Oh, okay. I thought nobody is there because everybody keeps quiet when I'm asking. Okay. For the tangent, it is actually you look at the point. Okay, you look at the point where you make the straight line with a point. Let's say you are looking at P1. Okay, so you need to make a 90 degree. Okay, a 90-degree angle. Okay, with this curve. All right, making 90-degree angle with this curve. So you make the straight line. Okay, you make the straight line touching this curve. So how to calculate that? So you can, let's say you can even take whatever, let's say in this example, so it gives you up to from T1 to T5. You can even take from T1 to T4, right? So it's not a problem. As long as your line, all right, your straight line here is making the tangent with the curve. So that's the concept of tangent. So tangent is actually you are making a straight line with the curve at 90 degree of angle. Okay. So you have Vx, right? So Vx is equals to, say for example here, you have 160 meter, all right? You divide with 4 seconds, all right? So you have the Vx over here 40 meter per second. So you look at the difference there, okay? You look at the difference. So between this, So you have the average velocity. As you can see that the when you are making actually you are looking at the instantaneous velocity, so actually it will decrease. Okay, it will decrease. Okay, when you're looking at the initial point. Okay, so how about, let's say, but this average velocity is actually giving you 75 meter per second, which is much higher velocity. So that means the let's say the object speed is much faster, right? So we have 75 meter per second. But when you look at the initial point, okay, it is actually starting at a very low speed. So what infers? What that infers? So that infers at the speed at the last point before the object stop, okay, before, I mean the last point, let's say here, for example here, is actually much faster than at the P1. Let's say here you consider that as the P5. Okay, meaning that the object here might be, okay, let's say here is 75, so might be here is 120 meter per second. So do you get the concept of the instantaneous velocity? All right, so you guys clear with the concept of instantaneous velocity?
Yes.
Okay. So also I need to mention that the average velocity is actually also decreasing when we look at the smaller point. Okay, I mean, if you start from the initial point where the object is moving slower, but let's say we are looking for the average velocity at point 2 to point 3. So what do you expect of the value of the average velocity? Anyone can answer me? Anyone can answer me? Shazwani?
Increasing.
Okay, good. So it should be increasing because the velocity increase much higher compared to previously, all right? From P1 to P2, let's say we define point here at P3, okay? So the average velocity from point P2 to P3 will be much higher than 55, okay? Should be around, let's say 65 meter per second, okay? So I hope you're clear with the concept of average velocity then instantaneous velocity, okay? Okay, last before not least, so all right, so over here I want to stress again the instantaneous velocity when we measure at the initial point will be slower, but at the end point it will be much higher. So actually that depends on the curve, all right, on the curve of the velocity against time. Okay, all right. So okay, so we look at different view of the graph. Let's say the object is moving like this motion. So okay, it's going from A to B and to C, D to E. So it's like that. Okay. So you are measuring the instantaneous velocity, okay, so over here you can see that, so it's making the tangent at every point, okay, making the tangent at every point. So you can see that here, when the object is moving along the path, that the instantaneous velocity can be positive, can be zero, and can even be negative, okay. But the average velocity here, as you can measure, let's say from point A to point E, is positive or negative? Is it positive or negative? Average velocity from point A to point E. Is it positive or negative?
See?
Yes, it's positive because the slope is positive from point A.
The slope.
Yes. So if, let's say, the point E is here, so the velocity will be negative. All right. So if slope is there, then the velocity is negative. But the instantaneous velocity can be positive or negative according to the path taken. For example, here, so we have the positive slope of the, when we're measuring at certain point. So we have the instantaneous velocity of positive at A, B, all right, and zero instantaneous velocity at C, and then negative instantaneous velocity at point D and E. Okay. All right. Okay, now we are looking at the motion. Okay. So this, okay, this is called as the motion diagram. Okay. So for the motion, okay, let's say first the particle is at x less than 0 and moving in the positive x direction. So we are considering the motion from this figure. Okay. So now we are considering, let's say, from this point, okay, from here. Okay, it should be from a negative, okay, from negative, so moving towards positive. All right, and then after 0, okay, after 0 it speeds up. You can see, so it speeds up, okay, from here, and then it speeds up to B. Okay, so here, as you can see, it's slow and then speed up to B, and then speed up again to C. Okay, and then after that it slows down, right? It slows down and then it stops. So it stopped at C. So that's why we are getting that. So it's going from slow and then speed up and suddenly stop. All right, suddenly stop, and then the speed decreases after that. Okay, when the speed decreases, so now the V is negative. So it is moving to the minus x direction. So you can see that the direction of the velocity change. Okay, and then it decrease faster. All right, it decrease faster until it will reach, okay, until it will reach again at, okay, at point E, okay, at point E, and until x is 0, okay, until x is 0. Okay, as you can see that. So here from the negative x, because here is positive x, okay, positive x, okay, and here is a negative x. Okay, all right. So that actually interprets this motion diagram, interprets this xt graph. Okay. Alright, so we have the concept of the average acceleration. So before this, so we have the concept of the average velocity. Okay, so the acceleration is the rate of change of velocity with time. So mean that we need to find out the delta velocity. Okay, before this, it is delta x. Okay, so now we find what is the delta velocity. Right, so the change of velocity at point 1 to point 2 over the time. So this is the graph. This is the equation. Okay, so let's look at the video over here.
In example 2.2, an astronaut is moving along a straight line, and her partner on the spacecraft measures her velocity every 2 seconds, starting at t equals 1 second. This table contains those measurements. Here's the column of velocities and the corresponding times. From this data, we'd like to calculate her average acceleration in various time intervals, for instance, between 1 second and 3 seconds, 5 seconds and 7 seconds, and so on. We begin by looking at a plot of these measurements. So here's velocity on the y-axis and time on the x-axis. And this point, for instance, corresponds to t equal 1 and v equal 0.8. And this point would correspond to 3 and 1.2. The average...
Okay, so you notice here that now the graph is in terms of velocity and time. Alright, so from velocity to time, and then you are measuring the change. Okay, let's say at t1, right? So at t 1 second, so over here, so we have t 1 second is 0.8. Alright, so you plot 0.8, and t 3 second, it is at 1.2, so you plot at 1.2. Okay, then you find out what is the delta velocity over the delta time. Okay, and then you move on. All right, and then you goes to 5. All right, so you keep adding the points to find out the average average acceleration. Okay,
acceleration will be the change in the velocity over time, and so it actually represents the slope of this line connecting these 2 points. And the same is true of the other 3 intervals. The equation we'll be using, of course, is this one, change in velocity over time, and it's now a simple matter to calculate the average accelerations on the 4 intervals by simply putting in numbers from the table. You notice that some of the accelerations are positive, others are negative. Also notice that when I plug in a negative velocity, I have to do a minus sign. For instance, there's minus a negative velocity, and that will turn out to be a positive here. But I just plug in the numbers directly, and the equation gives me the correct answer. Let's look at a plot of these accelerations versus time. The accelerations, of course, are constant, so they're going to be horizontal line segments on this plot of A versus T. And this one's positive, this one's negative, this one's negative, this one's positive. Let's consider the 2 negative accelerations. If I look at this plot, I'm starting at a higher velocity, around 1.5, going down to something like 1. meters per second. So clearly the astronaut is slowing down. And indeed, the slope of this line is negative. So that is a negative acceleration. But if I look down here, she's starting at about 0.5 meters per second and going up to something like 1 meters per second. So she's clearly speeding up. In this case, the acceleration is also negative. So you cannot determine the sign of the acceleration.
Okay, as you can see that the difference at point B and C, all right? So B, the velocity decrease slower. So you can see that the average acceleration is actually also negative. Okay, that's actually negative, but it is much slower compared to point C. Okay, whenever the velocity decrease faster, okay, your acceleration also getting negative, getting lesser. All right, so mean that the negative acceleration will be bigger compared to the point B. As you can see here, it is only at 5, all right, and then here, sorry, here it is only at, as you can see this graph, at minus 0.1, and let's say over here, so it is at minus 0.3. Okay,
solely by whether an object is slowing down or speeding up. You have to also know in what direction it's initially moving. And this ends example 2.2.
all right. Okay. Okay, now, okay, you are clear with the concept of average acceleration. So we also have the instantaneous acceleration. So as the instantaneous velocity, so we have similar calculation. So over here, we define the acceleration as A as, okay, equals to dv x over dt. Okay. All right. So the rules. Okay. So it is similar. All right. It is similar like the velocity. Okay. It is similar like velocity. So except that here we use the velocity for calculating the acceleration rather than we are using the position. Okay. All right. So to find the acceleration on the Vx t graph. Okay. So we have the velocity graph over time. Okay. So the concept is similar. Okay. We are looking at the, for the instantaneous acceleration, we are looking at the point where we need to make the tangent, right, with the curve. So you make the tangent. This point should be 90 degree with this straight line. Okay. So for the graph, so we look at different motion. So we have, let's say, a curve motion like this. So at a point A, okay, so where we have the velocity increases, so the slope is positive. Also B is positive. Okay, and then C, it will be vertical. All right, it will be a vertical line. So sorry, it will be horizontal line. So over here, the slope will be 0. So the instantaneous velocity acceleration will be 0. And then after that, the velocity decreases from point D and then decreases more at point E. So at point E, the negative acceleration will be bigger than D. So at point D, at point E, you will have the negative acceleration. At point A and B, you have positive acceleration. And at point C, you have the zero instantaneous acceleration. Okay, as previously, so we also have the motion diagram. Okay. So let's say the first one at a point A. So you look at the velocity over here. So this is the velocity. So it is from the negative velocity. Okay, from the negative velocity to 0. Okay, so the particle is moving in the negative x direction. Okay, the particle is moving in the negative x direction and slowing down. Okay, so why it is moving on the minus x direction? Because the velocity is negative. Okay, velocity is negative, as you can see. And then at point B, all right, at the point B, as you can see, this one is actually it okay, it is moving now towards the positive x. Okay, towards positive x. So from point B to point C, it will go to the positive velocity. So as I said before, so you have over here on the top here, so you have the positive velocity, and down here you have the negative velocity. Okay. All right, and now the particle is instantaneously at rest. Okay, at B, so you have the zero velocity, right? So you have velocity, the particle is at rest. Okay, meaning that the acceleration over here is constant. Okay, it's not increasing, it's not decreasing, but the acceleration is constant because you have a flat a zero velocity. Okay, a zero velocity. Okay, now the particle is moving in the plus x direction. Okay, it's moving from point B to point C. Okay, as you can see, again the velocity increase. Okay, velocity increase, and then its speed instantaneously not changing. Okay, the speed is instantaneously not changing at a point C. Sorry, at point C. So the speed is now not changing. At this point, at this moment, the speed is not changing. And then after that, the speed now going, okay, the speed now going to negative. All right. So when it's not changing, okay, of course, the object is at rest. Okay. And then now, going to change the direction, going to negative direction. Okay, from point C to D and then D to E. Okay, so that's the motion diagram for the instantaneous velocity. So you can see here the diagram for the motion diagram for the acceleration, okay, is actually much more complex compared to the motion diagram for the velocity. Okay, because for the motion diagram, you need to always show in terms of the x, which is the point. Okay, So you have the V, okay, you have the V and also the A, okay, on the motion diagram for the acceleration. But for velocity motion diagram, you only have V. Okay, so hopes that clear. All right, so we are looking at the different graph. As you can see here, so we have the positive slope, okay, from point A, okay, over here. All right. So we are considering back like the V graph, okay, Vx graph over t, but here we need to plot in terms of x. Okay, so we have the slope positive, so where Vx, the velocity is positive, the curvature is upward, so the curve upward, so acceleration is positive. And over here you see that the slope is positive, okay, slope is positive, but the curvature is 0. As you can see, it's not going, I mean the curve is not going like that. Okay, the curve stay, okay, and also it's not going like that. So you look at the curve, okay, the curve is flat. Okay, when the curve is flat, so how to detect that? So you need to draw the straight line. If the curve over here lie on that straight line, so meaning that your acceleration is 0. Okay, so you get the concept. So when the curve is flat, meaning that when you draw the straight line, the tangential line, okay, that the curve lies on the tangential line, so the acceleration is 0. Okay, all right. Okay, now you look here. Okay, the slope now is 0. Okay, because it's always horizontal slope, so now the slope is 0. And then curvature downward. Okay, curvature is going, okay, from up going down. Okay, going up, going down. Okay, you can differentiate here. So from here it's going up. Okay, now it's going down. Okay, towards that. So here it's going up. So here acceleration is positive, but here the acceleration is negative. Okay, the acceleration is negative. Okay, at a point D again, okay, you look at the acceleration again is a 0 over here. Why? As I said, at point B, because it lies on the straight line. The curvature lies on the straight line, which is the tangential line. Okay, but the slope is negative, so Vx is negative. So Vx, the velocity is negative, and at point E, acceleration again positive. All right, because you look at the E, okay, at E the curve is going up. Okay, it is going up. Okay, so you are clear with that. Okay. All right, so okay, the okay, last one, okay, before I stop today. So let's say we look at the motion diagram again. Okay, for this one. Okay, so for this one, we look at the motion diagram again. So we have, let's say, at the point A, particle is at negative. Okay, so you have positive x. Okay, and then you have the negative x. Okay, so at the negative, so you have negative velocity. Okay, you start at a point negative x. Okay, so moving in the x direction and speeding up. Okay, it speeds up. Okay, the acceleration speeds up, and then at point B, so the particle is at 0, moving x direction. The speed is instantaneous and not changing. Okay, so the acceleration is 0. Okay, and then we move more, so we have at TC. So TC, now the velocity is 0 because you have the flat slope. Okay, so you have this flat slope where the slope is 0, so the velocity is 0. So, and the particle is now trying to move in the minus x direction. Okay, so it's going towards there and then now move back. Okay, move back. So the acceleration now will be negative. Okay, acceleration now will be negative, and then moving to the minus x direction, and then at the point D, okay, is at the constant acceleration. At the constant acceleration, so we have ax will be 0, and then now the acceleration will be positive at point E because it will speed up again. It will speed up again, but the velocity is still negative because the slope is negative. Okay, so you can relate that. So when we have the x versus t graph, okay, when we have the x versus t graph, so we look at the concept of velocity and motion. So to define whether the motion is 0, positive or negative, so we look at the slope, which is the tangential line with the curve. And then once you draw that, and then for acceleration, you look at the curve with the line. Okay, so if the curve is going up of the line, okay, if the curve is going up of the line, so meaning that the acceleration will be positive. But if it is meshed, if it lies on the curve, on the line, so the acceleration will be 0. But if it is down, moving downwards, okay, moving downwards of the line, then the acceleration will be negative. Okay, so that's the summary of the how you can define the positive and negative of velocity and also acceleration. So that's it for today. Okay. All right. So last but not least, so let's take the picture for today. So for your attendance. So I hope you revise the slide for you to make further understanding on the subject. Okay, let's turn on your camera. Okay, so I'm counting from 10, all right? So 10, 9, 8, 7, 6, 4, 3, 2, 1. Okay. All right. So, okay, see you on next week. All right. So, any questions you can ask me on the WhatsApp. All right. So, Assalamualaikum and bye-bye.
Thank you.
Yeah, thank you, Doctor.
Thank you,
Thank you, Doctor.
Thank you, Doctor.
Okay, welcome.
Thank you.
Welcome.
Thank you, Doctor.
Okay, welcome.